Okay, so this is week 5, bonus track 3 I think, and we're on to the eccentric loading. So that's the secant formula. So if you recall the last problem we looked at, where we had a beam getting buckled, pushing down with a force P either side, and then we did an imaginary cut to expose the internal turning moment, although I should really be pointing it away, but it's going to be pointing back, and the internal turning moment and the internal force, which is going to be the opposite of the P. In this, and then we ended up with that our M, the internal M is minus Py, where this distance here to here is Y. P is being applied. We zoom in here. P is being applied at the neutral axis, and we're now going to do an eccentric loading where the P, we'll lower it a little bit. And that distance there is called E, the eccentricity. So we've got a little bit of E being applied there. This is an external force. If we go to the other end, we'll have the other external force being applied here. E, distance a bit below. This means that because these external forces are being applied not along the neutral axis, it's going to cause a turning moment in terms of the external forces. So we'll end up with an external force on top here, which is obviously will be turning in an anti-clockwise sense. So we've got an external force here, and we'd have one that's going to balance it on the other side. So as far as the internal situation goes, how does that affect things? Well, that just means that my internal force now will, if I focusing on this, so I've made the cut through the beam, and it's getting slightly deflected. The P, the internal force here, will be applied along not the neutral axis, but we'll apply it along this sort of offset E, so we're assuming that the thickness is staying the same. So that's where an internal internal force is being applied, and we will then just stick on to the M1. The fact that we've so if I shift this internal force down like I've shifted the external force down, that means that I can then now just stick on an additional turning moment, which will be created by the external turning moment. This distance from here to here is E, and that's P. So the external turning moment has a value of P times E, okay, in the anti-clockwise sense. So we've put in an additional turning moment there. We want this value to increase. If we're worrying about signs, we need to just think about what's going to increase my sign. So positive, depends how I'm defining y, but let's say we're defining y to be positive. Distance deflected, so distance from well, it would be, you'd have to sort of draw it further down, but the distance from here to here, that's your y. So your y is the distance from this line up to where it's getting deflected, and then a bit above that will be the neutral axis, E above that, and that's where we're applying the internal turning moment. So the internal turning moment overall will have this additional minus PE term added onto the end of it. So then when we come to stick that into our equation to work out how the deflection is going to behave, so EI, second order differential of y with respect to x. So we'll stick the internal turning moment in here, and we now see that we got an equation in the form of minus P1 y minus PE. So bring my y terms over to the left hand side. EI delta squared y over delta x squared plus Py equals minus Pe. So we've got a second order partial differential on this side. This will have the same solution as what we had before, so that's my particular integral. And my complementary integral here, this is a constant, so the trial function would be something like, the complementary function would be a constant. So we'll try putting in C there in a minute. So I know the I suppose I will rewrite this actually before I do this. So I'll rewrite this so that my leading term's got 1 in front of it. And I use that, my P, little p, I'm calling it P bar to differentiate it, squared equals big P EI. Okay. So I know the solution to that is, that's the particular integral, and it come in the form of A sine px plus B cos px. For my complementary function, I could do a trial of where it doesn't go any higher than a constant, so I'll do a trial of a constant. So the first differential is 0, second differential is 0. Let's put these values into here, and that gives us p squared c equals minus p squared e. So c equals minus e. So we've got a general solution of y equals a sine px plus b cos px minus e. So it looks very similar to our previous solution. We've just tagged on this little minus e at the end to take account of the displacement where we are at the beginning. Yeah, so at the beginning we are not going to be at the neutral axis, but we're going to be a bit below. Right, so far so good. What next? So the next thing we can do is to apply boundary conditions. When x equals 0, we've got our boundary condition. Actually, shall I do that boundary condition now? Yeah, let's do that boundary condition first. So when x equals 0, what do we expect y to be? And I suppose I would expect we're going to set y to put that at the datum, so we'll set that at 0. Okay, so that then gives me that b equals e. So that's my boundary condition 1. Boundary condition 2 will be when x equals L. And we'll set that again to be at datum 0. Okay. Right. So therefore I can rewrite that as a sine PL equals E one take away cos PL. What am I going to do next? Get rid of sine PL, and I'm going to use, no, I'm not going to do that. Okay, so yeah, I'm gonna use the identities sine theta equals 2 sine theta over 2 cos theta over 2. I'm using theta because x has already been used elsewhere, and I use the identity 1 take away cos theta equals 2 sine squared theta. So I use these two trig identities, and I'm going to substitute that into here. So that gives me a 2 sine little p L over 2, should be little p's, cos little p L over 2 equals E. Right, so replace that with 2 sine squared little p L over 2. So I can see that I've got a sine PL, which is going to cancel one of them. So that leaves me with A equals, the E is going to stay there. What about my 2's? My 2's are going to cancel. And I end up with a sine PL over 2 divided by cos PL over 2. So that equals E equals tan PL over 2. So I've now worked out my constants A, B and C, and we got the general solution. Y equals A, which is everything's going to be have a factor of E to it, isn't it? So we've got E tan PL over 2 times sine PX. B is just E plus cos PX, take away 1. That's my E there. Right, so I've got that. What next? Let's tidy this up. Or can we? No, we're going to leave it there. So we've got that. So the next thing is to say, when do I expect max deflection to occur? That will be when x equals half length. Okay. So we're doing the case where we're squashing from both ends, so half length. So sine PL over 2 plus cos PL over 2, take away 1. Yep. Okay, now let's tidy that. So that's going to be y equals E sine tan, sorry, is sine over cos plus, we got cos here. Right, so let's promote the cos so we've got a common denominator. So make that a square. Take away 1. So we've got sine squared plus cos squared all over 1 cos. So I get my final result. This is max. So y max equals E. 1 over cos is a sec. PL over 2, take away 1. Now let's go back and substitute. Remember, we're dealing with little p's, so little p's are square root of big P over EI. So we can go back and substitute that in there. square root big P E over I L over 2 take away 1. Rightio. So it's a bit of a mess. Can we improve on this? So we're considering basically the simple case. So that's our half sine function being squashed, where we've slightly displaced these points so that they're not acting down the neutral axis, they're slightly off center. So what is the critical force required for this case to buckle? Well, we called that critical buckling force, and we found that was pi squared EI over L squared. Okay. So let's look at getting rid of this EI and the L. So what I'm going to do is bring EI and L squared over to the left hand side and square root it, and that was going to give me and what do I have on the other side? So if I square root my pi squared, it becomes pi, square root my P critical, and then bring it over to the other side. So we've got this times this equals this divided by square root. So that leaves us with the pi, the 2, bring that out in front, and then we've got the applied force P divided by the critical force for buckling for the case where it's central loaded down the neutral axis, take away 1. It's good to say when we got to this stage, just make sure that your calculator, so I had the mistake that some people's calculators weren't in radians. So make sure your calculator's set to radians when you do this calc here. Just have a quick look at what we expect from 1 over cos take away 1. What will that look like? Well, cos looks like that. So sec is 1 over cos. So this is cos. This is a sec. So when you hit that this is 1, so this obviously happens at pi over 2. So when the force applied gets to be close to the ordinary buckling force, what's going to happen? So cos drops like that, sec will therefore go like that, and sec take away 1 will locate it at the origin. So when we have pi over 2 here, this looks a bit like a kind of exponential function where it zooms off to infinity when pi over 2 there. Okay. So what it's telling me is that I can't have a buckling that's approaching the can't apply a buckling force that's approaching the ordinary buckling force. When I start getting there, we're really going to zoom off and we're going to start buckling quickly. Okay, which is what we'd expect. Right, so that's the formula for the maximum displacement. Yeah, the last thing that we need to do is we need to work out the secant formula, which is related to the stress. So, is it worth stopping? We've gone for 25 minutes, so we'll stop there, and then we'll do another bonus video for the secant formula bit.